Okay, so now it's time for some really nice results about falseness and what this means. So we'll suppose we're working in a topos, although the first couple of results actually hold in any Cartesian closed category. And we're going to really understand a lot about the nature of initial objects. So we'll suppose that 0 denotes an initial object. So our first result we want to show is that the categorical product of 0 and any object A is isomorphic to 0. Okay, so how do we do it? Well, there's a nice simple proof to it. So what we want to do is show that there's exactly one arrow from 0 times A to any object B. So notice that by doing this kind of transpose operation, we get this kind of way of putting arrows from 0 times A to B in one-to-one correspondence with arrows from 0 to B to the power of A. So the number of arrows from 0 times A to B equals the number of arrows from 0 to B to the power of A, which is 1. So there's exactly one arrow from 0 times A to B. So that means that 0 times A is an initial object. Any pair of initial objects are isomorphic, so 0 times A is isomorphic to our initial object, and it's also, of course, isomorphic to A times 0. Okay, so now we come to a really cute theorem. This is Theorem A, and Theorem A says that if we have any arrow into an initial object from some object A into our initial object, then it follows that A is actually isomorphic to the initial object. So basically anything that has an arrow into an initial object in a topos or a Cartesian closed category, of which topos is a special case, anything in any case like that, whenever we have an arrow from an object into an initial object, the source of that arrow must itself be an initial object. So let's prove it. So we'll consider this kind of arrow, which is sometimes called the graph of f. So it's the arrow IDA, f. And now we just notice by the previous result that there's well, firstly, we know that every graph is a monomorphism. And secondly, we notice that there is, from the previous result, there's an arrow theta from A times 0 to A, because this is an initial object. And so it follows then also there's only one arrow from A times 0 to A times 0. And of course, if we do ID, f after theta, we get an arrow from A times 0 to A times 0, but there's only one, so it has to be the identity arrow of A times 0. So that means that theta here is the right inverse of ID, f, and that means that not only is ID, f a monic, it's also a split epic, and therefore it's an isomorphism. And therefore these two objects have to be isomorphic. But we know this one is an initial object, so since this is isomorphic to it, this must also be an initial object. It's isomorphic to an initial object. Okay? So then, now we're going to use those results to understand what the kind of nature of false and not are in a topos. So firstly, we know that there's a unique arrow from the initial object to any object A, and I'm going to call that 0A. And I claim that this is a monomorphism, and I claim it really represents the kind of empty subobject of A. So let's understand this. So firstly, 0a is a monomorphism. Why is that? Well, suppose we have a couple of arrows from some object h to 0, say x and y. Well, the thing is then in this case, by the previous result, we have to have that h is itself an initial object, and therefore we must have x equals y. So that means that 0a must be a monomorphism, because of course we have that 0a after x equals 0a after y implies x equals y, because x always equals y in this case. So yes, this is a monomorphism. And it makes sense to think of it as an empty subobject of A. So one of the properties it has is that if we have any monomorphism M, say from an object C to A, then we always have that 0A is in M. Why is that? Well, let's think about what this arrow 0C does. We have that M after 0C is an arrow from 0 to A, so it must be equal to 0A. So that means that 0A is in M. Okay, so just like the empty set is contained in any set, we have that 0A here is contained in any monomorphism. So I can actually write contains here. Okay. So we can also ask the other question, which is what arrows are in 0A? And so let's suppose that we have an arrow G from an object B to A, and suppose it's such that G is in 0A. Well, what's that mean? Well, what it means kind of explicitly is that there exists a K such that G is equal to 0A after K. But then the fact that there's an arrow K from B to 0 by our previous result implies that B itself is an initial object. And that implies that G is a monomorphism. And then the fact that we have this K means that we in fact have that G is contained in 0A. And we also have from this kind of result that 0A is contained in G. So in fact we have that 0A is equivalent to G. So this is a very cool result. It says that whenever we have an arrow which is in this kind of empty subobject, the arrow itself is also the empty subobject. The only thing in nothing is nothing. Okay, and nothing's in anything. That's what this says. Okay then. So now let's get on to applying this kind of stuff to some sort of logic. So we define, so for our initial objects, we have this arrow which we could call exclamation mark 0, or we could equivalently call it 0, 1. Either way, it's the kind of empty subobject of the initial object, if we like, and the classifying arrow of that is what we call false. So we could say that false is equal to chi of exclamation mark 0. Now, there's another way of defining false, often used in the Mitchell-Benerbau language, but it's equivalent to this. Okay. And now let's have a look at a nice result. So we know that when we have an arrow from an object that sends everything to true, we know that's the classifying arrow of the full subobject. Now what we're going to see now is when we have an arrow that sends everything to false, it's the classifying arrow of the empty subobject. So let's see it. The claim then is that whenever we have an object X, we have that false after exclamation mark X is the classifying arrow of 0x, this empty subobject of X. So let's see this proof. So we're interested in the subobject classified by false after exclamation mark X. So we know that this right square is a pullback square, and so the pullback lemma says that this left square is a pullback square if and only if this outer sort of black and red rectangle here is a pullback square. So in other words, we're going to have that this subobject denoted by this left vertical black arrow is going to be the subobject classified by FA after exclamation mark X, if and only if it's the pullback of exclamation mark 0 along exclamation mark X. In other words, if and only if this is a pullback square. And I claim that this is a pullback square. Okay, so I claim that if we put a 0 up here, then this square on the left here is a pullback square. Why? Well, firstly, does the square commute? Well, yes, it does, because these are both just arrows from 0 to 1, and there's only one such arrow. Now, secondly, let's suppose that we have some other arrow K, which is such that exclamation mark X. Now, secondly, let's suppose we have a candidate for a pullback. Let's suppose that we have this object K with an arrow L into X and an arrow U into 0, such that exclamation mark X after L equals exclamation mark 0 after U. Well, then we have to sort of construct this unique intermediary arrow to show that we have a pullback, okay, which makes this kind of left part of the diagram commute. So let's do that. So firstly, since there's an arrow U from K to 0, we can use our previous result to tell us that this K here is basically just an initial object. And now that implies that there's just a unique arrow from... So, I mean, basically I'm saying that because there's an arrow U from K to 0, one of our previous results said whenever we have an arrow from an object into an initial object, then the source of that arrow is itself an initial object. So we know that K is an initial object, so it just has to have a unique arrow into 0. And we know that this then makes this top triangle commute because U is just this unique arrow from K to 0, which must therefore be the composition of ID 0 after this unique arrow, which I'll call R, okay? And we have a similar kind of result at the bottom because, again, L is just going to be this unique arrow from this initial object k to x, and so of course that has to be equal to 0x after r, because there's only one such arrow. So yes, we do have this unique arrow that makes these triangles commute. So yes, this is a pullback square. So yes, indeed, the pullback of exclamation mark 0 along exclamation mark x is just 0x. So okay, let's use this now for some more practical things. So we define not to be the classifying arrow of false. Okay, so not, denoted by this kind of tilde here, is equal to chi fa, where fa is false. Okay, so suppose we have a subobject little a of capital X, then what does it mean to say not chi a is equal to true after exclamation mark X? Well, what's it mean? In other words, what kind of, in other words, when A is such that this is true, in other words, when A has a kind of in other words, when our subobject A is such that not chi of A sends everything to true, what does that mean about A? Well, we see here. So not of chi of A sends everything to true if and only if chi fa after chi A sends everything to true. And now this happens if and only if chi of A is in false, and this happens if and only if chi of A equals false after exclamation mark X. And then by our previous result, this happens, well, if we just look at this and then we say, okay, we have these two arrows from A to, then we say, okay, we have these two arrows from X to omega equal. Well, that means that the subobjects classified by these two arrows are equivalent. So we have that A is equivalent to the subobject classified by false after exclamation mark X, which we've just seen is 0x. Okay, so basically what I've just shown then is that we have that A is the empty subobject of X if and only if the classifying arrow of A sends everything to false, if and only if not of the classifying arrow of A sends everything to true. Okay, so one thing we want to do, there's something which we can think about, which is what's the subobject classified by not chi of A? Now, I think this has a name. I think maybe even different authors call it different things. I might have even seen some people call this the complement of subobject A, but I want to be wary of using that term because at least Colin McClarty uses the word complement to mean something quite different. So I don't know. I'll call it the negation of subobject A. So anyway, this is what I'm talking about. I'm talking about the subobject classified by not after chi of A. And so we might want to understand what this subobject is. For example, if we're working in the category of functors from some category C to set. We could use the Yoneda lemma to understand what kind of subobject this is, as long as we can understand what kind of arrows are in this subobject. So let's do that. Let's just suppose in our general topos, we have an arrow little h into x, and we want to know when is h in the subobject classified by not of chi of a. Well, we can see immediately that this is going to happen if and only if not of chi of a after h sends everything to true, which happens if and only if chi of fa after chi of a after h sends everything to true, which happens if and only if chi of a after h is in false, and false is just a point, so this happens if and only if chi a after h equals false after exclamation mark h. And then if we look at this, we can say, well, these are both arrows from capital H to omega, and so they're going to be equal if and only if the subobjects they classify are equivalent. So we have that chi a h equals false after exclamation mark h, if and only if the subobject classified by chi a h, which is the pullback of a along h, or we could say h to the minus 1 of a. So this here is the subobject classified by this arrow, and we're going to have that chi a h is equal to false after exclamation mark h if and only if this subobject h to the minus 1 of a is equivalent to the subobject classified by false after exclamation mark h, which is 0h, okay? So what's the bottom line here? Well, the bottom line is that we basically have that an arrow h is going to be in this kind of negation of subobject a, or whatever we want to call it. I mean, the subobject classified by not chi of a, h is going to be in that if and only if the inverse image of this subobject a along h is the empty subobject. Okay, so this gives us a way to determine, for example, when an edge is in a graph, or in general when an arrow is in a subobject, by looking at pullbacks.